Hello boys and girls, welcome to another episode of FoulkesBrau. Today on the bench we have two more treadmill boards to have a look at, kindly sent in to us by one of the viewers, John down in East London. So John, let's have a look at your boards and let's see what's wrong. So, right on the bench here we have our two boards, and I've just put them side by side so we can have a quick comparison. As we can see, they're both DCMD67 boards. This one's got a few more components populated. This one you can see those components are missing, not a problem. This one you can see has got a fuse in. This one you can see has got a wire link in. If we look at our little TNY266 from previous boards, you can see that one looks fine. That one has had the arse end blown out of it, so obviously we got a problem here. If I look at these two boards straight off, obviously this one is the upgraded one, but the revision numbers or version numbers stay the same. This one is SH-A94V-0 and that one down there is exactly the same, so the revisioning is the same. Funny enough, this one, they've got the little insulator pads over it, where this one they don't. They do those, yeah. They look the same, both in them, the two FETs, metal tab, and the two diodes, flyback diodes or clamping diodes are plastic tabs, so the diodes are insulated. Funny, there's nothing drilled into the cell pad. Other than that, the two boards look exactly the same. So let's start with the board that has got the TNY266 blown, because that is pretty simple, and we'll go through that one quickly, then we'll come back to this one. Right, so let us start with the board that's got the offline switcher blown. As we can see, we come in with live and neutral, we go through that fuse. Now there is a fuse that goes across there. Now I thought that that fuse in the previous video is actually protection for this circuitry. It turns out it's not. I've actually bothered to trace the circuitry. That fuse is for this circuitry down here, and you can see it's marked down and up. This is to raise the tilt of the treadmill. So if you want to change your gradient, run steeper, run less steeper, that's what this circuitry is for down here. So obviously it's not being populated on this board. On a previous board we looked at the transistors that are going there are they IGBTs or are they thyristors? I can forget. But yeah, so that's the big difference. And then you've got some optocouplers that are not populated, and some switch pads or connector pads, and then resistors and capacitors and things that go in there. That's about it. So there's nothing missing here. Obviously, if this is blown, we come through the live, we go through the fuse, the live branches off, it goes to this rectifier, because that TNY needs DC to drive this transformer. So the first thing to suspect that why this is gone is that rectifier. And why? Because I had a look at the data sheet of the TNY and recommended circuits, and it looks like that they've implemented this one for one. So what they're doing is that rectified DC, the positive side, with that leg down there, comes to one of these pads down here. I think it's that side, which they're calling the drain. And the drain is driven by an internal MOSFET. There's also an internal regulator that supplies power to the chip, and that internal regulator will have 5.8 volt regulated inside the chip, going to a bypass capacitor. The bypass capacitor, you can use an auxiliary winding of the transformer to power the chip and all sorts of funny things, but they're not doing it in this case. So what I'm suspecting, that regulator, when it went, now you will be passing AC through. That voltage regulator of theirs couldn't handle it, the capacitors or whatever that they've got in there couldn't handle it, and it blew the arse end of this chip out. So we know the chip is blown. There's no point going further, but what else is blown? I'm just going to put my multimeter to diode test, and we'll measure. Obviously you will hear the beep. We'll just measure the cross legs. Nothing there, nothing there, and nothing there, there, there. Could it be that this rectifier is fine? I doubt it. Let's switch the board over rather. And it's those 4 pads up here that we're looking for. Ah, there we go, dead short. If we swap it around, dead short. So that is on the 2 legs up here. So between an AC leg and the negative of the rectifier. I have got spare rectifiers. I don't have the T and Y. So I will have to order one of them. What you can do, let me just refix the zoom or the focus here, is go in and measure all these other little diodes, which I've already done down in here. The optocoupler circuits, diodes up here, down here, little voltage regulator up there, diode down here. I presume that's a 5 volt voltage regulator, but you can go through, measure the diodes to make sure that they are right, which I've done, so the diodes are fine. I will just give you an example. I'm going to measure one, and well, let's see if we can get in here. You see, you get a single beep. Fine. We'll measure another one. Single beep. Remember, that is in one direction. If I reverse the polarity, you won't get the beep, but okay. So everything else is fine with this board, just that rectifier. So let's have a look at the next board. Of course, you want to check these FETs, but I will show you that on the next board. Right, so here we have the board that has the up and down circuitry populated, as you can see, the 2 IGBTs or thyristors, whatever they are, isolators, opto-coupled isolators, and the connectors I was talking about, resistors, capacitors. Again, AC mains through the fuse. That fuse down there is for this circuitry down here. Little rectifier, we can see our TNY266, it looks fine. Transformer that this TNY266 is driving is that transformer to give us our auxiliary 5 volts or 5.8 or whatever it is, which will drive that regulator for this circuitry down there. Obviously we have feedback, and that will be that little optocoupler to tell this thing how it's doing. Must it give more power, less power, etc, etc, etc. Up here, bridge rectifier, relay, MOV. At the back end, you can't see it behind the capacitor, is the FET rectification diode. So nothing looks wrong with this. So let's measure across the fuse. The fuse is beeping, it's fine. We'll just measure the other fuse because it's there. The fuse is measuring fine. So what I'm going to do, we'll check the big diode up here, the bridge rectifier. I'm just putting one pin to the AC, one pin to the positive leg, if I can get it in there. Actually, it'll be easier if we just turn it upside down. So we're going to check that rectifier. AC to positive is fine. AC to positive is fine. Positive to negative is fine. AC to negative. AC to negative. So that is fine. Let's have a look at our middle rectifier down here. So these two are AC legs. AC to positive, AC to positive, AC to negative, AC to negative. Measures fine. While we at it, let us check our FET. Measuring between drain and source, and we'll swap it around one way, the diode, the body diode, so that looks fine. Let's measure this diode. Okay, so that looks fine. So let's bring the camera out a little bit. Oh, I can't do it while it's recording, so I'm going to just bring the lens out a bit and we'll have a squiz. That's a bit daft with this software. I can't change the lens while I'm recording. Hopefully they'll bring an update to the software. I'm using the iPhone 12 Pro Max to film this, and the software I'm using is Filmic Pro. So what I'm going to do, I'm going to switch my multimeter to resistance, and we're just going to measure the resistance across the AC terminals. 23 meg, 24 meg, 25 meg, that's fine. So we don't have a short across here. Let's just measure the resistance across the motor terminals as well. 231 kilo ohm, fine. Why I'm doing that? Because we don't see any obvious faults here. Remember, we go through our bridge rectifier, storage capacitor, bulk storage. Our FET there on the back is being driven by that gate driver down there, which is being driven ultimately by this microcontroller through some logic. So what I'm going to do, I'm going to solder some wires on there. We'll plug it into AC mains and we will come back and have a look and see what we see. Right, so I've soldered some wires on. Here's our plug. And let's plug it in and see what happens. Well, nothing went bang, which is always good. So we're going to measure some voltages, being very careful. So I've got my 240 across the mains. You can't, well, yeah, you can't. Well, if we move the board over. Okay, let's do that again. So I've got 240 mains across there. Let's see what we have across the motor terminals. I'm not expecting anything. Nothing. Okay. How about our voltage regulator? Nothing. 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 So we're not getting our output voltage. Okay. Could it be another TNY that's gone? Well, let's see if we measure the chips. If we measure that TNY266, let's measure pin 1, let's measure between pin 1 and the source, which is going to be pin 1 and pin 3. So I'm first going to put it to AC. I'll come around the other side. We can go to pin 1. Millivolts. And pin 2. Also millivolts. And switch it to DC. .9. 4.9. So that chip, could be under voltage. I don't know. What does the data sheet say? It's got an internal. Okay, the bypass pin under voltage circuitry disables the power MOSFET when the bypass pin drops below 4.8 volts. And to understand how we get that 4.8 volts, we need to see what do we have on the drain. I will show you the, perhaps let me set that up and then we can have a look at the schematic together, and then I can show you what I'm talking about. Right, so here we have the data sheet, and it shows us the typical application circuit. What we can see is our positive and negative rectified AC, so that tiny little round rectifier comes in through the transformer. That is great. We have a little voltage divider resistor that comes and gives us our enable voltage. This goes through an internal regulator and gives us our bypass voltage. So the enable will be fed through that resistor on startup, and once this transformer is running, we rectify it and we smooth it. We come down through a Zener diode down here, and then through an optocoupler here that will give us our feedback to enable this thing to switch. So on this point we're getting 4.9 volts. Now the data sheet speaks about 4.8, so 4.9, 4.8. It must be greater than 4.8. Let's say that this internal voltage regulator is not working. Well, let's have a look at the block diagram. This is actually very simple to see. We've got our power coming in through the drain pin to a 5.8 volt regulator. That drain pin is internal to the chip. It's this MOSFET here internally. So the drain pin goes through a MOSFET to the source. So our positive of our regulator rail, our rectifier rail, to our negative rail of the rectifier. The drain gives us our 5.8 volts, and it goes out that way to the bypass pin where we're measuring 4.9 volts. What we have here is we also have this enable or under voltage pin. Now basically this enable comes through this AND gate, goes through auto restart, counter goes through, goes to this current limit state machine. I wouldn't worry too much about that. What we are worried about is this under voltage. If we follow that under voltage back, we'll see we've got a current source here, a current source here. Now this under voltage, if it's not there, or if we're not getting the right voltage, what it could be is it could be that this optocoupler is gone. It could be that that resistor has gone, or that capacitor, or this chip itself. So the only way to know is, let us measure what we're getting here on the enable side. That Zener diode, well, I don't know what it is, but we can have a look what should be there. So we can measure the voltage we're getting on that side of the Zener. We can measure the voltage we're getting that side of this on the, put it like this, on the cathode, the anode. We can measure what's going in to this optocoupler, and basically we can see what we're getting on the enable. So we'll start with the enable pin. We already know the bypass is giving us 4.9 volts. And obviously we want to see what is on the drain, because on the drain we expect 300 and something volts if we're taking straight AC. So let us have a measure. Right, we're back with our board. So let's see, just to recap, we're going to measure the bypass pin. And the bypass pin is, we're going to measure between source and bypass of pin 2 or 3 and 1. 2 and 3 and 1. We're getting 4.9 now. We need a minimum of 4.8. So let's say our multimeter's right. We're telling the chip, hang on, the voltage is too low. Okay. Let us measure on the enable pin. So source to enable. So source to enable is 2 or 3 to 4. Be very careful when you're doing this, please. There is some very nasty stuff here. So 2 to 4, we're getting 2.1, 2.2. So we're definitely getting voltage there. We're saying, hey, please switch on. Right. Our drain pin of this, in other words, pin 5, as we saw in the data sheet, is powering our 5.8 volt regulator inside. So let us see. Now be very careful with this, because I'm expecting a minimum of 320 volt DC here. And how do I get to that? Well, it's mains voltage, in our case in South Africa, 230, 240 volts mains, times the square root of 2, because we need to go to the peak value. We're taking the RMS value, the AC value, and we're getting the peak value, because that is what DC really is. And so I'm going to measure between the drain and source here. So I'm going to measure between pin 5 pin 5, 2, 3, 8, and 7. So we'll just measure all of them. So pin 5 is going to be our drain. Let me just get in there. Wait, we said 5 is our drain. We just put the leads the right way around, otherwise you're going to read negative values and see what's going on. So 5 to 2, 325 volt DC. And what did I do? Because that LED just switched on. Did I short pin 3 to 4? I did. And what are we getting on our enable pin now? .7 volts. So let's just measure that again. We want 2 to 4, which is our enable under voltage, 2 to 4. .8 volts. So we come here and we measure, we will be getting our, yes, our voltage. 3.3, so obviously for that regulator. So 3.3 on the microcontroller. But why did it switch on? Let's have a look, see on the optocoupler, 0.9. And on this side, that'll be feeding our chip. I can't really get in there. Not nicely anyway. Nothing. Let me try from the other side. No, I am getting something, 0.9. So 1. and on this side 0.9. Could it be that our optocoupler's gone? Let's pull the plug. There, everything switches off. We'll put the AC back. And there it switches on. So what I'm going to do is just measure here. Again, be very careful here. So we're measuring quite a bit of voltage there. It was drain to source on the FET. Nothing on the gate, I don't expect anything. What I'm going to do, I'm going to unplug it, leave it for a few minutes to let all the capacitors discharge, and then we'll come back and plug it in again. What I'm thinking is somehow there is a loose connection there, because I don't think I shorted, because we were measuring between 2 and 4. So basically we were shorting the under voltage to ground. If I did short it, and I don't think I did, but it is possible. Just out of curiosity, what are we measuring on the bypass pin? So that'll be between 2 and 1 or 3 and 1. Let's have a look. 2 and 1. Now we've got our whole 5.8 volts, none of that 4.9 volt rubbish. So I'm going to switch it off, let it discharge for a few minutes, and then we'll come back. And of course, as luck would have it, I've plugged it back in and it powers up. So I definitely don't think it's that switcher that's got a problem, and I don't think it's the optocoupler. The only thing that I can think is that the capacitor on the bypass pin is maybe a bit leaky. And so I am going to replace it and check for dry solder joints, but I don't suspect anything else. The only thing really that is there is that bypass capacitor, so I'm suspecting that multi-layer ceramic has got a bit of a problem. So what I will do is I will take it out and we can check whether the capacitor is okay or not. One thing I want you to be very aware of, I'm going to unplug the mains, and what I've got, let's just do that. So if you can see it, I've got my multimeter hooked up to the negative terminal of the motor, the tab of that FET at the back, and that tab is just the drain. It's the common point of the drain of the FET. So I'm going to unplug it. You can hear the relay switch off. Here's the plug. You can see it's the same leads, and look at that voltage. And that is all because of this bulk storage capacitor at the back. So be very careful when you work with these things. They do keep the voltage for quite a long time. What you may be able to see is at the back there, there's a little green LED, and it's bleed resistor. Now that bleed resistor is quite big. I think it's a couple of meg. So this capacitor is going to take quite a few minutes, probably about 15 minutes, 10-15 minutes to discharge if you look at the rate that it's going. Now what you can do, I don't like doing it, is take a metal bar and short the capacitor out. Yeah, you put a bit of stress on the capacitor. Ideally what you want to do is put a resistor across there, quite a few ohms and quite a bit of power. So I'm not going to do any of that. I'm just going to let it discharge naturally. What I will do is take that capacitor out. We can have a look at it and then we can see what it's doing. Because the way that this chip works, if for whatever reason it goes below 4.8 volts, it needs to see 5.8 volts on that bypass pin before it will unlatch. Now, if that capacitor is leaking, it would never have seen the 5.8 volts. Remember, the drain of the chip, the drain chip, goes through our voltage regulator, which gives us our 5.8 volts. So if that capacitor was leaking, then you're never going to get that 5.8 volts. You're never going to unlatch the circuit to enable it. So that is what I suspect has happened. So I'll take that capacitor out and we can have a look-see together on the ESR meter. Either way, I'm going to replace it. Right, so we have the capacitor out of the board, and yeah, it is a bit flaky. Anyway, let us test this capacitor. So I'm using my LCR meter. We don't want it in auto. We want to measure the capacitance, we want to measure the series capacitance, and we want a frequency of 120 Hertz for measuring the capacitance. So according to the marking on this should be a 100 nanofarad capacitor. So I'm going to put my leads across it, and we are measuring 1/10 of that. We are measuring a whole 8.5, and we can also have a look at the equivalent series resistance, not at this frequency though. So we step the frequency up, ten ohms, and dropping 8 ohms. Okay, settling around 8 ohms. Let's measure that again nicely for you. Okay, this capacitor looks like it's okay. So roughly around 7 ohms, 7.8 ohms, and 8 nanofarads. So the capacitance is way too little. The data sheet calls for 100 nano. So I actually have a very nice capacitor down here. Again, ceramic, but rated for 100 volts, but it is a COG filling. So if I measure the capacitance, we're close enough to 100 nanofarad, but you can see the resistance is, the ESR is quite a bit less, 2 ohms less. So what I'm going to do, we'll put this capacitor back in, and we will come back. Right, so we're back, and we can see we've replaced this capacitor down here with that capacitor up there. If you look closely at this capacitor, you can see where the leads go in, where the legs go in. It's actually damaged, and that wasn't me. And it's reading 1/10 of its capacitance. So the only thing left to do is to switch it on. So let's plug it in and see what happens. Is it gonna go bang or not? No, there she powers straight up. Excellent. So we'll just put my leads on. We'll see, we're measuring voltage on the gate of the FET, and then we'll come down and take some readings on the T and Y. We'll put it to DC voltage and we'll plug it in. So we've definitely got voltage on our FET gate. That's fine, we're happy with that. And let's measure the voltage on the enable and bypass pins as we did before. I don't expect any trouble there, but we just want to make sure. So we remember source is pin 2. So I'll come around to the other side, and our enable is pin 4, our bypass is pin 1. So let's come around like this. I'm not in your way. So we'll go to pin 2 to pin 1, which is the bypass. 5.8 volts, perfect. And what you heard there was me pulling the bypass to ground. That's why the relays went out. There, you hear that again. That's me dropping it, so I shorted that. But normally 5.8 volts, perfect. So, and then we want to go to the enable under voltage, which is pin 4. And we've got a whole 1 volts there, 1.04. Perfect. So definitely our system is working. So I suspected that capacitor was very, very leaky and we had problems. I'm just going to put it in back to the FET. Again, be careful, and you can see it's not quite at the 380 or 320 volts yet, because that bulk capacitor takes a long time to charge up. So what I'm going to do, I'll unplug it. You should see the LEDs and everything go off. The relay's clicked out. There, the LED's gone quite dim, although we've still got quite a bit of voltage on the board. We'll plug it back in, and there she is, back up and running. Okay, so this board is done. I'm happy. What I will do is I will let it run. I will let it run probably for 48 hours or so. Every now and then I will unplug it and plug it in to make sure that it switches on. But definitely I think the bypass capacitor that we replaced down there, and why I say that is, remember initially we measured 4.8 volts on it, 4.9 volts, and I don't think it was getting back to the threshold. So, and even when we measured it on the LCR meter, we could see that the capacitance was 1/10 of what it should be, and that's definitely a no-no. And also obviously the ESR of it, so I think it was a bit leaky. So yeah, interesting. What I will do for the other board, we'll end this video here, but I will order the T and Y for the other board. I have the rectifiers, that's not the problem. That's the T and Y, and they're a bit of a schlep to get in South Africa at the moment. So what I'll do is I'll see if I can get the TNY 266. If I can't, I'll replace it with a TNI DCMD67. So we'll end this video. We'll close up now. And so we come to the end of another video. Rather interesting fault on that board. The bypass, or what they're calling bypass capacitor, basically had deteriorated or given up the ghost. So a bit more interesting than the usual faults that we're getting. The second board or the first board, I will order the TNY266 and the the rectifier I've got, so not to worry about that. I don't know that we'll come back and make another video of it working, because we've done that in a previous video. Unless there's other faults in it, I'm not going to make another video of it, because it's a straightforward replacement. Desolder the chip and replace it, and that's it. So anyway, I hope you found that enjoyable. I hope you learned something. I hope you had fun. It helps to sometimes have a look at the data sheet and the application circuit and see what they're trying to do. It will give you a good idea of where to look. Anyway, take care, be safe. We'll catch you in the next one. Cheers.